afternoon. And we're really excited to bring you the next session of our webinar series on scientific computing infrastructure for life sciences. Just to let everyone know, the slides and recording of this session will be sent immediately following the session. So if you're interested in getting the slides, we'll get those out to you right after this. And if you have any questions during the webinar today, please use the Q&A feature in Zoom. I'm going to be in there answering questions in real time as I can. And at the end, if time allows, we might do some live Q&A, but we wanted to kind of focus on the content today, make sure we can get through all of it. Chris is known for having a lot of slides, so we're going to get right into it. So today our speaker is almost needs no introduction, Chris Dagdigian. He's one of the co-founders of BioTeam and our senior technical director of infrastructure. He spent most of the last 20 years designing, building, and improving research-focused HPC and IT systems for use in demanding production computing environments. And so the topic for today, as you can see, is AWS ParallelCluster. We're going to share some tips, tricks, and lessons learned from direct experience with our clients. And so, Chris, take it away.
All right, appreciate it. Thanks a lot, Adam, and hello, everybody. Thanks for attending. Let's see if I could advance my slides. All right, so what I've typically done here is I want to focus here on basically how I broke up the content. We're going to talk a little bit about traditional HPC on AWS, why in particular ParallelCluster is a nice solution. And then I broke up the main focus of the talk materials into a couple of different sections: operational considerations, persistent essentials, things to think about when you want to change node configuration, things to think about post-deployment or pre-deployment, and then finally the most common acts that we find ourselves doing on a parallel cluster, sort of post-install and post-deployment. This actually might be the beginning. There's a lot of interest in sort of scientific computing, license-aware scheduling, Slurm APIs. This might be the beginning of a sort of multiple event series where we talk specifically cool stuff about ParallelCluster. So if this is a topic of interest, definitely send us feedback. This might not be the this might be the first of many webinars that we do in the future. And then finally, I do want to acknowledge the AWS HPC team, the ParallelCluster developers in particular. This talk is a lot easier and a lot less of me whining about things I hate because of the hard work of the ParallelCluster developers, who are basically every day they seem to put out a new release that makes my life easier or sort of removes a gripe that I've complained about in the past. And then a number of the operational things I'll be talking about are influenced by people inside BioTeam like Carl Goodwin and Adam Kraut. So I wanted to specifically acknowledge them as well. Most of you are here. I think you're here to hear about ParallelCluster. You don't want a long introduction from me. I think Adam did a very good job sort of setting the stage. So what I wanted to concentrate on here is that this is not an overtly slick high-level talk. This was really attempting, we're going to try to brain dump very quickly and very deeply sort of all of the things we've learned sort of using ParallelCluster since back in the CFN days. So I'm not an expert in this. I'm not a great programmer. I'm not a guru. There's very likely technical errors or mistakes in these materials, and 100% of them are mine. And then finally, the slides, if you've seen me deliver 80 slides in 40 minutes before, my slides tend to be word heavy and I tend to deliver them very quickly, more often than not because the PDFs of the slides live longer than the actual event. And so we constructed this slide deck with the assumption that the PDFs might get passed around. So there's going to be a lot of words I'll be throwing at you. The other thing that we found is I sort of assumed that the attendees of these events were all like BioTeam friends and family, people who've known us for forever, but we started talking to attendees of previous webinars, and quite a few of them had no idea who we are. They were drawn to the webinar because of the technical content. So I wanted to put a couple of slides in here. Again, I'm going to leave them in mostly for reference because I'm worried about time. But for those of you who are drawn by the words ParallelCluster or Cloud HPC who don't really know who BioTeam is, at the end of the day, we're a group of scientists and technical people who had to learn a lot of hardcore technologies in order to get our research done, in order to support our customers. We sort of built a consulting company around that. We're 20 years old this year. We started from 4 people. We're now 50 people. One of the best things about growing a company is as BioTeam has grown, I've been able to demote myself in the org chart so that I can stick doing consulting and the work that I love rather than running business and doing sort of suit type stuff. I think the reason why we're around after 20 years is that there's a lot of consultants out there who are motivated to sell you specific things. We made a very conscious decision early on in our career when we started the company that we aren't going to profit based on the procurement and purchasing decisions of our customers. So on the HPC side, I have customers who've invested 6, 7, 8-figure sums in storage, HPC, lots of stuff. And it's important that they understand that I'm not getting a referral payment, a commission. We don't sell or resell hardware, things like that. So if the quick high level dump of BioTeam is basically, we're an objective vendor and technology neutral consulting company built from scientists and technologists. All of us at BioTeam are sort of deeply curious, and all of us are sort of highly motivated to make the world a better place. And so if that sounds interesting to you, read the next couple of slides, drop us a line. I'm Chris@bioteam.net. I'm pretty easy to reach. And that's the end of the sales pitch. There's a couple of interesting marketing slides that I don't know well how to talk over, so I'm just going to skip past them, to be honest. Skip that. All right, so where we are in the presentation here is I wanted to sort of set the stage and really sort of talking about why, and in particular, because ParallelCluster recreates what I would consider traditional HPC on the cloud. And sometimes there's some questions about why you would actually want to do that. The blunt truth is that basically a lot of the cloud marketing and online materials still tends to lie to you. When you read these rosy case studies and these rosy reference accounts and you talk to cloud salespeople, all of them treat legacy use cases and legacy patterns as basically embarrassing things that very few of us really talk about. They all tend to pretend that we're going to rewrite everything that we do from a cloud native architecture using best practices. They tend to assume that DevOps and infrastructure and code and automated CI/CD pipelines are pervasive and used throughout R&D and enterprise IT. And then finally, they sort of assume that our scientists are surrounded by a cloud of expert cloud engineers and cloud software developers who can sort of make all of their problems go away. None of that is true. And this probably resonates with you if you're an R&D IT person or an IT person. So there is very much a need for what I consider traditional HPC on the cloud. If you're talking data intensive life science in particular, we have hundreds, if not thousands, of applications, scripts, utilities, wrappers that are simply never going to be rewritten for cloud native, serverless, object storage only design patterns. We also are heavily dependent on tools and algorithms, some of which are peer reviewed and published and change very rarely, that always assume that storage is presented in kind of a files and folder view, which means we have sort of a tremendously sort of long tail. I think the future of scientific data at rest is object storage. It's going to take us forever to get there because we have this long tail chain of dependencies of tools and applications and basically systems that expect to see storage presented as files and folders. The third point is the reason why I like traditional HPC is that the scientists that I work with, typically they've already learned Python, they've already learned Bash, they're probably also doing R, and all Python and Bash in particular are highly repurposable in a traditional HPC environment. If you need to script or glue together a pipeline, if you need to manipulate or munge data or sort of clean up results, the skills that you learn regarding Python and Bash are directly transferable. Whereas, the cloud native stuff, I don't want to have my scientists learn the AWS, serverless application framework. I don't necessarily need them to learn how to code the AWS batch or develop, complex container orchestration strategies. So I think it's a combination of skills, support, legacy tools and practices that still expect POSIX presented storage. And then finally, we have hundreds of scripts and utilities that are, there's just no time, no resources, and really no benefit to rewriting for a cloud native architecture. So if you buy if you buy my argument that traditional HPC is here to stay on the cloud, this is where ParallelCluster comes in. So ParallelCluster is just magic. I mean, it effectively recreates, if you come from an academic environment, a commercial industry environment, a nonprofit environment, or even from one of the DoD or US government supercomputing sites, or even NIH, you are very familiar with the concept of a shared storage layer. You're very comfortable with the concept of a compute farm, and you're probably comfortable with a batch scheduler. It might not be Slurm, but it might be Grid Engine or PBS or one of the other ones out there. So AWS ParallelCluster is the easiest way for you to recreate the traditional HPC capabilities in the cloud in a way that is deeply familiar to IT administrators, IT operators, and even our early career, mid-career, and senior scientists. Many of us have already been exposed to these systems before, either in university, at the NIH, or on premise-based systems. But finally, the other thing that ParallelCluster does is it takes the sort of legacy HPC capabilities and it adds all of the cloud magic. The particular cloud magic for me is auto-scaling. I can have a cluster of really expensive compute nodes that scales down to a compute fleet size of 0 when there's no work in the Slurm queue. So for me, ParallelCluster is the best of both worlds. I get POSIX, I get a shared storage system, I get a batch scheduler I know how to work with, but I get magical stuff like auto-scaling where I only have to pay for the compute when I'm actually running jobs. So at this point, I feel like I'm still talking fast, but where we are in the deck is now I want to sort of transition you into sort of our brain dump of things that we've learned over the years. So the first thing I really want to talk about is the operational philosophy. If you come from a premise HPC environment or a government supercomputing site or the NIH, or if you're an IT person who does HPC, you will know the immense struggles that we have to build a monolithic HPC stack that is concurrently used by different competing users, groups, projects, and applications. There is a tremendous amount of time and effort built into tuning the batch scheduler and tuning the cluster to be most serviceable for the broadest array of users and workflows. And the way I describe it is that you have to tune the HPC environment to piss off the smallest number of scientists at any given time. And that's a lot of work. The biggest sort of aha moment for me with ParallelCluster was realizing that that sort of monolithic shared HPC environment, that model does not have to carry over into the cloud. It is now very easy via ParallelCluster to run multiple clusters. Each cluster can be perfectly tuned, perfectly configured. The compute fleet size, nature, and configuration can be perfectly tuned to whatever metric you want, whether it's a per user cluster, a per project cluster, a per application cluster, or a per department cluster. The biggest mindset for me is I've moved away from the massive concurrent shared single monolithic HPC stack to now I run purpose-built custom designed HPC clusters, and I might be running half a dozen of them at any given time for a particular biotech client. So this mindset is fairly game-changing for those of us in HPC who've spent blood, sweat, and tears trying to configure Grid Engine or Slurm to sort of make the most number of people happy and the least number of people, sending angry emails to our bosses. The second thing is that if you read a lot of cloud art literature and marketing, there's a lot of stuff about disposable infrastructure. And, I feel like sometimes there's an overemphasis on how cool it is to, instantiate infra on demand, use it when you need it, and then just blow it all away. That works really cool if you're a cloud native cool kid and everything you've done is best practicey and multi-account and serverless. But in my world, the consumers of AWS ParallelCluster, they're scientists. They're scientists doing batch parallel interactive work. They need persistent stuff that lives independently of any single sort of cluster that I might give to them or take away from them. So in my mind, the second sort of take home message is that there's stuff that you're going to want to persist. And for me, cluster life is 100 times better or 1,000 times better when I have three persistent things. Number one is I need a consistent way to resolve user identities and authorization in many cases. Number two is I need a persistent and durable place for my users to keep their home files and folders. And then finally, I also need a persistent and durable way for my scientific applications, my tooling, my pipelines, my commercial software installations. I don't want to put them in the operating system because the operating system in ParallelCluster could go away if the cluster auto scales down to nothing but the head node. So I kind of want three essentials. I want identity, I want home folders, and I want a place to store centrally installed and centrally mastered scientific applications. And the take home message here is these things should live independently of ParallelCluster, and you should be able to attach them and detach them to ParallelCluster as you need and as you sort of deploy and operate clusters over time. So, this is kind of, there's a couple of different ways that you can do these persistent essentials. My message for you is the solution for identity is there's no one answer. The answer is whatever operationally works for you. The green stuff up there is what BioTeam typically does. One of the fantastic newest features of ParallelCluster is it comes out of the box now. If you have an Active Directory environment, you can natively launch with LDAP support. That's transformative. I've already switched probably a dozen clusters over to that method by now. The second thing we've done is when we don't have a central identity store, we'll use something like Ansible to create local users and groups. And then finally, there are clearly environments where I have to configure in a different LDAP server or like a free IPA cluster or something like that. And again, we would typically do that via Bootstrap scripts managed by ParallelCluster custom actions. There's other ways to do it. You can copy an Etsy password shadowing group from an S3 store if you wanted to. And then finally, the last resort thing is you can stuff a custom image with whatever weird bespoke stuff and whatever weird InfoSec agents that the security team is forcing you to put into your Linux machines and things like that. The solution in my case for home and apps, and when I say solution, I mean the starting point. For me, the starting point is AWS EFS. EFS is a nice NFSv4 protocol. It's really easy to attach and manage and use. It's my starting point. The two downsides to EFS is that you are definitely going to have use cases where EFS is not performant, either millions of tiny small files, or you're just hammering your EFS file system and the scientists start to complain. The issue there is that EFS performance tuning is still an arcane art. I don't even really think I understand it, and I feel uncomfortable throwing money at provision throughput. It's just a deeply confusing thing for me. And then finally, the other downside is that when you do a DF to see how much space is available on your EFS share, it tells you 8 exabytes. And when you give a scientist a file system that says 8 exabytes available, they're going to take that as a challenge, and they're going to stuff terabytes, if not hundreds of terabytes, of random stuff into your EFS share. And so I have a couple of customers where, a couple of months after deploying this, we suddenly had 400 terabytes in EFS and no one really knew what the heck was going on. So I do want to mention here that, data management and data strategies become important. This is a big focus of BioTeam's consulting work as well. Beyond a certain scale, you're going to want to have a human managing data. And I see some chats as well there. I guess the other thing I should mention is that EFS is the starting point for me. There are other alternatives to move to when EFS is not performant. FSx Luster is the sort of AWS native way to do it. I really like systems like Weka.io that I can plug in interesting sort of external storage layers as well. But I think that the take home point on this slide is my starting point is EFS. That's probably should be your starting point as well. And then you move away from EFS if business, scientific, or throughput demands require. That could be moving to a Luster file system, or that could be moving to instance types that have local instance storage and doing a lot of scratch partitions and teaching your users how to migrate data off of EFS to local instance storage. They hammer the local instance storage, then they write the results back out to EFS. So there's a lot of things around storage and making storage performant. And I think really my only lesson learned here is you start with EFS and then you move away from EFS when business or scientific demand requires. Just a couple of pictures here, and I might sort of skip this over, but basically this is just showing you what it looks like on the command line for the first picture is showing you GID values coming from an Active Directory LDAP, and then the second things are sort of showing you basically the output of module aware. In particular, one of the reasons why I'm showing you the screenshot that it's at the bottom of this slide, the one with where you can see NAMD in text, is that centrally managed scientific software that lives outside of the operating system is important. And for those of you in IT and leadership who don't understand, on the science side, we might have 8 different versions of R, 4 different versions of Python. And as you can see here, I have 2 different versions of NAMD comprising 5 different flavors of how NAMD was compiled and built. So when you start thinking about the complexity of scientific software and environment, the other persistent thing you want to have is a central way to manage and master, including the ability to support multiple versions of the same program on the system in a way that your users can easily flip back and forth. So that's why for me, the starting point is EFS with environment modules, and that sort of sets the stage for some interesting things that I can deliver to scientists. So where we are right now, I want to kind of do a recap. We sort of covered the operational philosophy and the 3 persistent things I think you should have. That's all covered here. The mental shift is you don't have to run one HPC in the cloud. You can run many tuned for different requirements. Don't be fooled by any marketing or evangelism you see around everything on the cloud needs to be disposable. There are certain persistent things that you want to have. For me, it's identity, it's home folders, and it's a central managed place to install scientific applications. So moving on now, this is probably the biggest section of the talk. I want to say, like, one of the coolest things about ParallelCluster is every time they come out with a new release, they remove an annoyance or a to-do or things that I sort of spent a lot of time manually doing. And so I really want to bluntly say that ParallelCluster 3.2 deployed with EFS and AD LDAP integration comes as close as possible to zero-touch post-deploy as I've ever seen. So now what I'm showing you here is I want to talk about the typical things that we need to do. Like as awesome as ParallelCluster has been at removing the zero touch or removing the things I need to do to touch post deploy, there's still stuff that I need to do. So I want to walk you through the things that I typically do when I do post deployment stuff. So typically, this is kind of a running list of, even with EFS and LDAP integration, I still want to install a couple of packages into my nodes. I probably want to create a login banner that my users can use when they log in. If I have environment modules living on an EFS share, I need to configure a local configuration file so that environment modules knows to search EFS for managed applications. There's a particularly annoying GID error that I see in LDAP environments that I often want to fix. And then finally, my scientists treat their compute nodes as digital laboratories, and I spend a lot of time making sure that they have sudo access so that they're empowered to do what they need to do on a compute node. So if you think about the history of node configuration, particularly if you've been doing this stuff on the cloud for a while, in the early days of CFN cluster, it was kind of hardcore. I'd have to read the documentation, pull an AMI ID, make sure the AMI ID was from the right region, manually launch the image, manually stuff all the stuff I wanted into that image, rebundle it into a new AMI, then cross my fingers and hope the cluster launches without a fatal rollback error. ParallelCluster 2, and I'm not exactly sure where this feature came, like when it came in, but ParallelCluster for a while now has had this fantastic ability where it can install itself onto an AMI that you create. So if you have a trusted AMI, or you're using EC2 build pipeline to build trusted AMIs for your organization, there's a very good chance that there's a particular build model with ParallelCluster where ParallelCluster can install into a custom AMI that you develop. And then finally, the golden age for me is, parallel cluster with this custom action stuff that I'm going to show you later is sort of transformative for me in terms of reducing what I need to do when I need to touch a node. So the only thing I do want to say is I will never shame anybody for making custom AMI images. I did that for a very, very long time. However, if I'm honest with you about the downsides, it's not really the time sink. That's manageable. The issue for me is whenever I built custom AMIs for Parallel Cluster, I effectively pinned or froze my cluster environments to that very specific version of Parallel Cluster. And so the end result is I have a lot of older pharmaceutical and biotech customers that are running very old versions of clusters because it still works. And we haven't been able to sort of generate the inertia that we need to make a change. And so my biggest advice here is to really try hard to avoid making a custom AMI if you can. There's no shame if you need to, but the biggest risk with a custom AMI is I find that it sort of, it has the danger of pinning me to a specific version of Parallel Cluster, which then makes it harder to upgrade and leverage a new feature. And you really want to be able to upgrade because the rate at which Parallel Cluster is coming out with new features is just really, really impressive. Again, I'm a little bit worried about time. So really what I want to talk about node configuration here is that these are the key hooks that we use. There is a custom action hook, and in particular within custom action, you could run a script as root right after a node boots up. So that's where you do all of your Chef bootstrapping, your Ansible bootstrapping. That's when you change your DNS resolver to point at a custom VPC resolver or whatever. The second hook is even more interesting. The hook for on node configured runs after the system is up and running and on the network. And that's when you could do stuff like change or alter the Slurm configuration. The most beautiful thing about this custom action is that these custom actions are available at multiple locations in your Parallel Cluster config file. So you can run custom actions on the head node. You can run custom actions on the Slurm queue level, which means you can have different scripts that run on your GPU partition versus your high memory partition versus your standard C6 compute node partition. So I really want to stress the value of this custom action capability, in particularly the two hooks, on node start and on node configured, and the sheer number of places where you can drop those configuration steps into your Parallel Cluster. This has been transformative in that I no longer make custom images for Parallel Cluster. This is sufficient that I can bootstrap all of my stuff, and it's fantastic. It's wonderful. I'm going to talk a little bit about my favorite node configuration method, but I don't want to push I don't want to push a particular tool at you. The thing that has worked sweetest and smoothest for me is pulling Ansible playbooks out of a code commit repository. It's just magic in the way it works, in particular because the Git authentication is handled at the IAM level. So I don't have to worry about credentials and secrets and API keys and tokens and SSH things and things like that. The reason why I love it, and again, this is not meant to be an Ansible sales pitch, it's just that the YAML files for Ansible are super approachable. They're very easy to read. Even if you don't understand Python, you can kind of get a sense of what's going on. But the most beautiful thing here is the number 2 bullet point. An Ansible pull method using code commit can be reused everywhere that I run Linux. I've used the same playbook and the same method when I'm building trusted images in EC2 image builder pipeline that I'm distributing to multiple Amazon accounts. I use it on all of my bog standard Linux machines like that RStudio or that Jupyter Notebook server I built for a scientist. And then finally, the exact same code and the exact same method is Parallel Cluster. So there is an incredibly beautiful thing about having your node configuration framework be consistent and identical across trusted image builds, across your hand-built servers, and across your programmatically deployed parallel clustered nodes. And finally, the item potency nature means I can constantly run and rerun these commands, always bring my nodes into sync. I can use a SSM session manager to send out an Ansible pull command to nodes that are running. They will automatically configure themselves to the desired state. I don't have to rebuild or destroy or replace that Jupyter Hub server or that RStudio server that's been kind of running for a while. So it's just a beautiful thing. I really do find the combination of Ansible pull from code commit to be the sweet spot for doing node configuration. In the interest of time, I'm going to skip over a lot of this stuff. The reason why we're putting this in the slides, if you kind of want to see how we do it, how we set it up, and why we do it, it'll be in the slides after the talk. I'll pause here and say my goal here is not to show you IAM permissions for code commit. The thing here is I want to say one of the mistakes that I made in the past is I made IAM policies that were overtly too tightly scoped and too tightly scoped from a name. So anytime, if I had an S3 access policy and I wanted to add something new to it, all of a sudden I would find the name of my IAM policy no longer matched what the policy was allowing. So my take-home message here, and it's a little bit confusing, is I like the idea of creating a generically named IAM policy. And if you see the bold text at the bottom of the slide, this policy is inside something that we call BioTeam automation enablement. a policy name called automation and enablement is significantly generic enough that I could put code commit, I could put S3, I could put the KMS permissions I need to use encrypted session manager stuff. And so recommendation here is don't be too specific with your policy names when you're working with ParallelCluster. I really like the idea of kind of like a generic enablement policy that you can change and modify and sort of enhance over time. I just want to pause here and show you how simple our bootstrapping script. So when I talked about custom actions with ParallelCluster, this is our primary custom action. We install 2 Python packages, and then immediately we're able to run Ansible pull to download our playbooks, and then the Ansible playbooks do the rest of the work. The final step in this script is that we actually download the Ansible pull scripts to the local operating system so that an operator can manually run the Ansible update commands if he or she wants. I'm not going to talk about this slide except to say if you are in a multi-account world, and more of my accounts are using shared services accounts and shared services VPCs, there's some extra steps that you have to do if, for instance, you want to pull from a code commit repository that's in a different Amazon account. I've documented it here. Ben Kehoe's utilities make it relatively simple to do an assume role pivot in a bash script and pull that code commit repo from another Amazon account. This was the last major headache that I had, was sort of doing parallel clustering, kind of a complex multi-AWS account environment. I am absolutely going to skip the closer look at our Ansible playbooks because I'm a little bit worried about time. So forgive me as I go through here. But if you're interested in what I actually do to a compute node, including fixing LDAP and fixing things like that, then at the end of this talk, you can go through the slides. And again, I'm Chris at BioTeam.net, happy to answer questions. So where we are right now, and I apologize for shotgunning and talking super fast and dropping audio on you, is we're sort of at the end of the node configuration thing. And I'll just kind of recap node config in the way that I recapped the other things. So the current state of ParallelCluster with EFS and LDAP integration is really close to zero touch, but there are still always going to be things that you want to do after it's deployed. It is very easy to deploy ParallelCluster into an existing AMI image if you have a reason to use a custom image. We've talked about the pros and cons of doing that. And then finally, I think the nature and flavor of the custom action hooks is so powerful for me that I no longer have to build custom images. I can download an Ansible playbook to do whatever I need to do on a node, and my scientists can read the playbook, my IT people can read the playbook. It's just a beautiful thing. So I am not going to shame, and I'm not going to talk smack about custom AMIs. I've used them, I've built them, there's absolute uses for it. But if you can, the value of going to a purely bootstrap method via custom actions is that you can more quickly ride the ParallelCluster release roadmap, and you can more quickly leverage all of the cool features and capabilities that they're rolling out. So now I'm moving into sort of actual deployment consideration, things that I think about when I'm setting up to deploy or when I'm deploying a bunch of parallel clusters. The pcluster docs are very specific about this, so this is obvious, but always install ParallelCluster into a dedicated Python virtual environment. The single biggest reason is that if you upgrade ParallelCluster, you might lose the ability to control or manage older versions of the cluster stack. So that's just an absolute sort of no-brainer thing. Always put ParallelCluster into a Python virtual environment. You should probably name the Python and virtual environment so that it has the ParallelCluster version in it, so you can switch between them. And then something that bit me last week, the Python version actually matters. The latest version of ParallelCluster drops support for Python 3.6, which is kind of painful if you're using CentOS 7 to manage your HPC fleets, because Python 3.6 is the last supported Python in CentOS 7. Fortunately, I had Python 3.10 already built from source, and I was able to move on. But you got to read the fine print sometimes, and especially if you're using older distros, sometimes you might find your Python is a little bit too old to play with the ParallelCluster cool kids. The next thing is, this is a mistake that I'm guilty of. I love the power of being able to deploy ParallelCluster from my laptop. The problem is that in order to manage or change a cluster, someone's going to need access to the config file that you launch the cluster with. So you can't hoard these files on your laptop or on a system that only you have access to. So option A is, it's very common for me to build a sort of super cheap T3 micro or whatever. We put it into the VPC, we name it HPC operations box, we put a bunch of Python vends there, and we all share that machine when we manage ParallelCluster. The other option, if you're in a CI/CD culture, automation culture, is it's not too hard to train your mind and body. Just always take the live version of the config file, push it to S3, push it to Git, push it to Azure, repos, whatever you use for version control. The key take-home lesson here is don't hoard the YAML files on a machine that only one person can get at. You'll have operational problems if you do. The second thing here, and this is a little bit controversial, I spent a lot of time, every time a new version of ParallelCluster came out, custom writing IAM policies down to least privilege, and I had different policies for deployer and stack and user. It took a lot of time and error, and the end result is that, again, I had IAM policies that were specific version of ParallelCluster, and I had to spend a lot of time updating them every time. if you are willing and able to deploy parallel cluster from an EC2 instance or a person with admin-like permissions, then parallel cluster actually does a really good job of writing its own IAM policies and roles. They're also very well scoped and fairly secure. I would say, they're actually secure. And they're also custom specific. So the roles and policies go away when you destroy the cluster. So I am actually a fan of deploying parallel cluster with high levels of permissions that allow parallel cluster to write its own IAM roles and its own sort of tightly scoped IAM policies as well. And I suspect parallel cluster is going to get better and better at writing sort of tighter and more secure policies as they sort of progress down their release roadmap. I'm a huge fan of additional IAM policies. There's things I always add. I'm a big fan of SSM, so I'll traditionally add the SSM thing. If you're going to use the Slurm mem.sh script, which sets real memory values on your Slurm partitions, then your head node is going to need EC2 read-only access so it can query the API to learn, how much memory that P2 extra large, that P3 2x large instance had. So additional IAM policies is I don't want to say underdocumented, but it took me a while to discover this, and then I fell in love with it, and now I attach all sorts of policies. And you can see that last policy that we attach is the generic BioTeam automation enablement one. That's the one that contains KMS, S3, code commit, and all of the other sort of operational permissions that we would want our cluster to be launched with. I'm a very big fan of tagging. It's been a cloud hygiene thing since forever. There's no excuse not to launch parallel cluster with a really good set of tags. And I'm going to point at you, webinar audience, and hopefully you do have a tagging policy and configured set of cost allocation tags, in particular because it's possible to use parallel cluster in very expensive ways. And you're going to want to have cost reporting and cost allocation tags set up if you want to make your management and your sort of scientific leadership happy. Another thing, this is a quick one, is it's worthwhile to review the monitoring section in your parallel cluster config file. If you don't tell it otherwise, it's going to keep your logs for 14 days. I think in the earlier times of parallel cluster, I found a lot of log groups that were created with sort of never expire, which was a little bit wasteful. So I basically my lesson to you is I go between 1 day and 14 days retention based on whether or not this is a test cluster or a production cluster. And then typically I set deletion policy to delete, because at the point where I'm deleting a parallel cluster, I really don't care about the CloudWatch logs. And it's cleaner for me hygienically in my AWS environment if I wipe the logs at the same time I wipe the stack. There is a got you with AD LDAP integration that bit me when I ran an internal BioTeam training class. The long and short of it is you got to read the fine print. My recommendation is if you want to use parallel cluster with LDAP, you should have a real domain controller. The domain controller should be in your VPC, or it should be on your premise, reachable via direct connect or however you attach to the cloud. The gotcha with using AWS Managed AD is that it is incredibly painful to set up encrypted LDAP. So painful that you're probably encouraged to turn off LDAP encryption altogether, which is a really, 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 really bad thing to do. So basically, that's all I'm going to say about this. But right now, until AWS makes it easier to talk encrypted LDAP to managed AD, my recommendation is start with a real domain controller, or otherwise you're going to have to do things like SSL terminating load balancers in front of managed AD. And it's not hard, but it's just one more operational thing I'd rather not have to worry about if I could avoid it. The only reason I discovered this is I set up managed AD for a BioTeam training class that we ran internally. And then I realized that I didn't want to set up a load balancer. And so we did the training class with unencrypted LDAP. Don't do that in production is basically the lesson I'm trying to tell you. So that's where we are right now. I kind of went over the deployment configuration or considerations, and let's sort of recap that a little bit. So recommendation number one, and this is straight out of the parallel cluster docs, it's not from me. Always put your parallel cluster installs into a Python virtual environment. You don't want to hoard those parallel cluster config files. They should be accessible on a shared machine or a Git repo or an S3 bucket. You really do want to think about IAM, and I do now favor deploying with admin-like permissions so that parallel cluster can write its own IAM policies. Number 10 is important. Like I said, I always add SSM. I always add that BioTeam automation enablement sort of generic policy that contains a bunch of catch-all stuff like code commit access, KMS key permissions if my session manager stuff is encrypted, S3 buckets that I want my cluster to be able to access, things like that. Number 11, again, no excuse. You should be deploying fully tagged clusters. The clusters should be tagged according to your standards. If you don't have a standard, you want to have a standard. If you don't have AWS cost allocation tags set up, you really want to set up cost allocation tags so you could do financial reporting based on your HPC usage. Number 12 was just minor. You might want to tweak the retention and deletion values for your CloudWatch logs. And then finally, 13 is the thing that bit me a week or two ago. There's some encrypted LDAP gotchas that you have to consider if you're using an AWS managed directory service inside the AWS account. final, I want to talk about post deployment. And I realized when doing these slides, it really boils down to things I haven't automated with Ansible yet, or things that I don't do often enough that justifies Ansible automation. The single biggest thing I do on every parallel cluster deployment is I set up accounting. To an IT person or a technical operator, this might seem useless or unneeded, but it's absolutely critical for the users, the users of these systems. You want tools like Ceph and saccount to actually work. Users need to be able to query the exit status of jobs that are no longer active. And in particular, if you're building cluster environments where you are having Slurm enforce memory usage, if Slurm is going to be killing jobs based on the user job exceeding their memory allotment, then you really want to give tools to the users that they can use to check their memory usage and sort of help profile their work. And you can't do any of that unless you have accounting set up for Slurm. There are other things that I do on a case-by-case basis. I would say maybe 20% of my parallel cluster deployments use memory-based enforcements. The point at which you turn on memory-based enforcement is when you have user jobs that are stealing all of the memory on a compute node, taking away resources from other users, and probably invoking the Linux OOM killer, which starts nuking processes, including jobs from people who were submitting jobs the proper way and the nice way. That doesn't happen in every environment, but when it does, you really want to turn on sort of Slurm enforcement of memory-based management. And that gives me the opportunity to talk about that last bullet point where I used to go into every cluster and turn on memory enforcement. Parallel Cluster 3.2 shipped with that as a native feature now. So that's an example of how great and how sort of responsive the Parallel Cluster development community is. They're slowly chipping away at the list of things I do by hand. And the current 3.2 release, I haven't tested it yet, now has the ability to turn on memory-based scheduling in Slurm. And going back to that middle bullet point again, there are also sometimes some weird stuff that we do to Slurm clusters. I support a lot of molecular modelers and computational chemists who use the Schrodinger suite, which is very expensive. It's FlexLM licensed. There are 30-person biotech companies that pay $1 million a year to Schrodinger for licenses. And so it's very important to make Slurm license aware. It's very important to turn on license aware job scheduling and integrate that with Schrodinger so that jobs don't run unless there is a license available, and we can keep those $1 million software assets constantly cycling, so there's a good ROI on the CompChem investment. I do that rarely enough that I don't do it to every cluster, but I would say 60 or 70% of my clusters run computational chemistry workloads. So Schrodinger license-aware integration is something we've done often enough, and I think we're going to do a webinar about it specifically because it's become a sort of particularly popular request about BioTeam. So I've talked a lot about this already, so I'm not going to read this except to point you at the red text. It used to be a lot easier to set up accounting because Slurm would let you say, I want to store accounting data to a file. Here's the file path, go do it. Somewhere in the last release or two of Parallel Cluster, they updated the version of Slurm, and the version of Slurm that's in Parallel Cluster 3.2 seems to have taken away the ability to do file-based accounting. So now it's kind of a pain in the ass, to be frank. I actually have to set up a MySQL server if I want to enable accounting, which basically, practically speaking, I don't like. I come from Grid Engine, decades of using Grid Engine. I've been storing accounting data and text files for forever. It's never been a sort of operational concern for me. So it's a little bit of a pain in the butt now that I have to set up an SQL server if I want to turn on accounting with Slurm. Hopefully I'm wrong about that, but I couldn't figure out a way to keep file-based accounting. So the reason why accounting is important, and this is an example of Ceph output. Unfortunately, I didn't capture good CPU utilization for this particular job, but this goes back to my Grid Engine days too, where one of my pet peeves was the number of tools available to administrators versus the number of tools available to end users was really out of whack. Ceph and the accounting files are one of the few user accessible things that a user can do if she wants to profile her job or see how jobs have exited, or in particular, if you're doing memory-based enforcement, you're really going to want to be able to have Ceph so that you can see how much memory your prior jobs ran. This will allow the scientists to build up their memory profiling knowledge, and that will allow them to submit future jobs to Slurm that make proper memory requests, rather than asking for all of the memory in the node, or rather than making gigantic requests that make it hard to schedule into the system. So again, this is something that IT and operational people often don't catch up on, but the lack of user accessible tools for job information and job profiling is sufficiently sparse enough that I'm a strong proponent of enabling accounting on every parallel cluster that we deploy. And the way the slowed roadmap is improving, I'm guessing this is probably not going to be an annoyance of mine for long, but it's just a huge value. Like, accounting unlocks It doesn't all, it unlocks things for me as administrator, but primarily it unlocks things that are valuable to your end users of the system, in particular, being able to look at past performance and resource consumption of jobs. I tend to take a different approach with MySQL depending on my environment. If you're a heavy parallel cluster shop, if you expect to run a lot of HPC environments, it makes sense to stand up RDS MySQL. It's not expensive. You can run a single zone, non-clustered MySQL service. None of none of the data that's stored in the SQL data store is particularly valuable or unique. You could recreate it or recreate the databases if you had to. The other cool thing about the way Slurm does accounting and the way Slurm handles databases is one RDS instance can support many MySQL databases. So you really only have to run one RDS, even if you're running 6, 12, or 20 parallel clusters. The second bullet point there is there are times when I don't feel like setting up RDS, or maybe I don't think it's worth the cost. In a sort of throwaway or disposable model, or even a small cluster environment, it's perfectly appropriate to drop a MariaDB or MySQL server on the login node and configure things locally there. And again, the last bullet point is I'm not going to force you one way or the other. The right choice is the one that works best operationally for you. The other less frequent things that I do, and again, this ties into, this is basically, this is a list of things that might be future webinars. If you're interested, send us feedback. But, I do have to do a lot of sort of load sensor type scripts when I want to talk to FlexLM license servers, parse the output and update Slurm so that Slurm knows how many licenses are available on any given second. The second bullet point I've started to do, it's become I think 3 people have requested that I enable it. Slurm actually has a RESTful API. It's not installed with Parallel Cluster by default, although the source code is there. You can compile it and enable it if you want. If the idea of having job control, job submit, and job monitoring from a RESTful API is of interest to you, Slurm could do it, and you have to just set it up. And that's become a little bit of a slightly popular sort of post-deploy thing that I do for some customers. Old school HPC people are probably familiar with XDMOD. It's one of the sort of really nice ways to ingest, store, and report long-term on very, very large clusters, including accounting data, usage data. It's becoming slightly more popular, especially when people have millions of dollars worth of Schrodinger CompChem licensing floating around. You actually want to set up some sort of persistent reporting and dashboard for how are your HPC resources being consumed, what's the job exit status, what utilization are you getting out of that expensive GPU or ML cluster that you stood up. XDMOD is kind of the starting point for that. And then finally, this is embarrassing, I just discovered pcluster.cloud, which is a web stack for managing and accessing parallel cluster environments. I haven't even touched it yet. I just poked around at the website, but if the idea of a web management console for parallel cluster is of interest to you, point your web browser at pcluster.cloud. It actually looks pretty interesting. This is the last thing. I think this was the last slide I wrote because I woke up this morning realizing I forgot. If you read a lot of documentation about how to set up Slurm accounting, or in particular, how to create databases in MySQL, a lot of the online information starts with configuration descriptions that start with grant all. It turns out in RDS, you are rarely allowed to grant all. And I've seen this on Oracle. I've seen this on all sorts of, so if you try to grant all on an AWS RDS MySQL instance, it's going to say heck no, and it's going to deny you. So this last slide here is showing you from my notes, my actual grant statement that I had to use when I was creating the Slurm accounting database. So grant all was not allowed, but it turns out that the grants you need to make Slurm accounting to report are fairly straightforward. It's select, insert, update, delete, drop, alter, create routine, and alter routine. So if you give those grants to the database, you'll be good to go. This is just a sort of throwaway take-home lesson because, again, I got burned so many times on Stack Exchange or Google or reading documentation trying to figure out why grant all is not going to work with RDS. So those are my notes on the grant statement that actually works with RDS and works with Slurm. All right, so that's kind of the end of the post-deployment act. And I feel like I went really fast, but I think we have like 15 minutes left before we hit the top of the hour. And Adam, I think I'm ready to actually throw it over to you for questions and comments. I do apologize for blowing quickly through the Ansible stuff, but like I said, I really wanted to get to the end and sort of hear from others and then sort of queue up future webinar and future questions. So Adam, I guess I'll just throw it over to you. And before I do, I just thank you everybody for attending. I really appreciate you guys taking time out of your day to show up for this. Oops. There we go. That's the end of my slide. Everyone. And Adam, I don't think I can hear you.
Can you hear me now? Hello? No? Checking.
If I can't hear you, Adam, maybe we could take it to chat or something else.
Can you hear me now? Weird.
Oh, all right. So Alicia can hear Adam, but I can't. So let me mute myself.
Okay. Hopefully everyone can hear me now. Maybe.
Thumbs up. Okay, they can. Ben says we can. So yeah, so all right. So yeah, I just kind of wanted to go through a few of the questions that came in, just kind of touch on some of them. So the first one was from Ben Carr, and I think you did answer it live, but we can bring it back up. He says, I need EFS to be too slow. So we're looking at things like FSX for luster.
Any recommendations on EFS tuning? So yeah, Ben, I think you're thinking in the right direction. Like luster is certainly, better for scratch and sort of for the performance heavy stuff. And also I think Chris mentioned instance types that have ephemeral storage that you can set up as scratch, which pCluster will do automatically for you. Is definitely a way to kind of work around the EFS bottlenecks. I don't have any sort of magic for EFS tuning personally, but I don't know, Chris, is that kind of your opinion as well?
Yeah, I would say the path of least resistance for EFS IO issues is maybe first to look at data staging with ephemeral instance stores, just because it's really easy to do data staging and you kind of get that for free if you launch the right instance types. But that being said, in the same way that I'm sort of praising the parallel clusters for the rate at which they're the parallel cluster developers for the rate at which they add new features, the AWS HPC team and the Luster people are going nuts improving Luster under the hood. So I would say the starting point for a performant file system for parallel cluster would be FSX Luster. It's just you need to think about it. You need to think about how you're going to operationalize it and create it and maintain it. And it's definitely going to be fast, but operationally, it's a little bit harder to get your head around than EFS, particularly if you have enterprise IT people on your team who are comfortable with NFS, but have really never sort of seen a parallel file system with HSMs and things like that under the hood.
Yeah, totally. Okay, so Wenlang says, can you speak for AWS batch processing in comparison to parallel cluster?
Yeah, I think the only thing I will say about batch, and Adam, you can correct me if I'm wrong, is that batch is fantastic. And I have 2 customers who are directly using batch for genomics, in particular with Nextflow and a few other sort of bioinformatics pipelines. However, the reason why I'm talking exclusively about Slurm is my focus is on legacy HPC and sort of recreating the premise-based HPC environment in the cloud. And for me, legacy HPC is I need that batch scheduler, I need that Slurm or that grid engine or something like that. So the only thing I will say is AWS batch is awesome, but you've got to program against it, and it's a skill set, and it's less likely that I'm going to get an early career scientist who knows batch, but it's highly likely that I'll be working with an early career scientist who's been exposed to Slurm before. So that's really my focus is on Slurm, mainly because of the legacy needs.
Yeah, totally. I would agree with that. It's that traditional HPC environment that people are really accustomed to using, and so it's kind of a path of least resistance. And if you have a greenfield project, I would say definitely look at targeting batch, because it also means you're going to use things like Docker. So yeah, it's definitely a different migration path, I would say, and it's going to take a little more effort than just picking up pCluster. So awesome. All right, what about we've got someone says, what about integrating nice DCV or open on demand with pCluster?
Yep. So I'm actually not familiar with Open on Demand, but nice DCV I'm very familiar with. ParallelCluster in particular makes it very easy to integrate with nice DCV, and in particular that pcluster.cloud URL. It looks like they have an interface for DCV as well. But candidly, what I'll say is most of my pharmaceutical and biotech customers are coming from an environment where they're more familiar with things like NoMachine. So it's actually more common for me to stand up a GPU accelerated shared Linux desktop running NoMachine. And I bring my users to the NoMachine instance, and then they access the cluster or the graphical tools from there. So this is a long-winded way of saying I really like nice DCV, but based on my customer demand and experience, more often than not, I do a NoMachine graphical desktop rather than going with the nice stuff.
Awesome. Okay, someone asks, what scale Slurm clusters have you worked with? Number of cores, number of jobs per day, number of users?
Yeah. That's a loaded question because it brings up a lot of pain I'm having with Amazon right now. So, our work with NIH and TAC and others, 60,000 cores, tens of thousands of active jobs, thousands and thousands of users. I mean, we know Slurm can scale. On the cloud, the thing that's been killing me is it used to be that GPU resources were in really hot demand. So I put a lot of new biotech and pharma customers on the cloud. And the last time I created an Amazon account for someone a couple of months ago, we were limited to a single GPU instance, and our quota on non-GPU instances was like 32 virtual cores. This is a long-winded way of saying, realistically on Amazon, my older customers would run thousands of cores, maybe dozens or many tens of GPU nodes. But the thing that's killing me now in modern times is I cannot get the number of GPUs and the compute nodes that I need on Amazon because of how fiercely contested resources are. A particular issue came up yesterday is I have a stealth mode biotech startup that has a very compelling business need to run on 400 CPU cores. They want to run 50 compute nodes, each with 8 virtual CPU cores. They've exhaustively profiled their algorithm to run under Dask to support that model. Amazon would not increase our quota for 400 virtual CPU credits. The best I could get out of them was 300. That's probably a sort of reflection of the fact that this is a new Amazon account, new customer with not a long tail history. But anyways, I feel bad. I would say on premise, we work with tens and tens of thousands of cores. We work with some of the biggest supercomputing sites in the world, NIH, TAC, Department of Energy, things like that. In the cloud, I would say my older Amazon customers are running hundreds or thousands of nodes, but there's this gotcha where my newer pharmaceutical biotechs, they're running a dozen GPU nodes, or they're running half a dozen metal machines, or a small number of very large memory machines. And honestly, it's not because that's what they want to be using. It's because what Amazon's been quota limiting them to. I'm sort of hoping that the supply chain issues are going to go away, particularly with GPUs. But I have a major issue right now with AWS and quotas that is starting to hammer some of my HPC using customers.
Yeah. So, and following up on that, where do you go if US East 1 is a dumpster fire?
So I've already relocated one biotech. So I have a biotech customer in the Boston area that was spending $80,000 a month on EC2, and they were denied a quota request for a single additional GPU node. We basically tore down their VPC and we built them in US West 2, the Oregon region. More common than not, if I'm dealing with an East Coast biotech company, we will consider building them out in Ohio. Generally speaking, US East 1 is where most of the resource constraints I find are. So if I'm putting a new customer on Amazon, or I'll take an existing customer and we have to go GPU hunting, the two regions I recommend if you're US based is US West 2 in Oregon is decent, and then US East 2 in Ohio is also decent. It's more likely that I'll be able to find a GPU node in Oregon or Ohio than I will be in Virginia. And the problem has been significant enough that I've actually relocated biotech environments out of Virginia and dropped them into Ohio or Oregon, or we've kept them in Virginia, but we've built out VPCs and transit gateway attachments into other regions. This is outside the scope of ParallelCluster, but if you're talking scientific computing on Amazon, one of the things that you need to build into your architectural planning now is you might have to go region hunting for scarce resources, particularly if you have a GPU heavy requirement. It's very, very difficult to get GPUs. And in fact, you'll probably see us talking at BioIT World next year, where we're starting to see customers pull back from the cloud and build GPU clusters in co-location facilities, or even pulling GPU clusters back on-prem because it's been so difficult to get them. And it's not an Amazon specific thing, it's an Azure resource constraint as well. Cloud-based GPUs are in an incredibly contested demand given the rise of crypto mining, in addition to AL, ML, machine learning, vision, natural language progression or processing, as well as all of the comp chem and MD sim stuff that we on the life sciences side need to do.
Got it. And last one, or I guess this is just kind of a request for future presentations on AWS batch and use cases in the future. So I think that's great feedback. Yeah.
Yeah, we would definitely be interested in that. And one of the things we really like about these webinars is the feedback that we get from the audience. So, I might not be the best person to talk batch, but there are other BioTeam people who can talk batch at length. And it might be kind of cool in the same way that I'm talking Slurm and ParallelCluster. Maybe we can combine batch with talking about Nextflow or some of the other sort of common work, frameworks out there. So yeah, keep those comments coming. And there's a lot of really interesting BioTeam people who are sort of hands-on and a lot of interesting technologies. So if there's something you want to see us talk live about or demo, definitely drop us a line or shoot us an email.
Cool. Yep. And one line just confirms, yep, Nextflow, CWL, SnakeMake. Yep, we've used them all and evaluated many of them. So yeah, that's a great topic for a future webinar. Okay, how about would a private cloud provide any advantage over an on-prem system if GPUs are needed?
So private cloud is a loaded term. To me, it used to mean running OpenStack on-prem or a colo. I think so. I'll use private cloud as just a catch-all for a cloud environment that's hosted outside of the major cloud providers. The short answer is yes. The long answer is yes, depending on your data transfer speeds or your data transfer requirements. The easiest way to say it is that terabyte to petabyte scale data transfer into and out of a cloud environment is really, really expensive. Amazon lets data come in for free. They meter and charge for data coming out. So it turns out that there's a lot of scientific workloads that are CPU heavy and data light. So for instance, if you had a private cloud or a co-location environment and you could shift all of your chemistry, your structural biologists, all of your molecular modelers, maybe even some of your other GPU users who aren't, using multi-terabyte or multi-petabyte, training sets, if you can carve out a piece of your workflow that is CPU heavy and doesn't require terabyte to petabyte volumes of data exchange with a cloud provider, then I think private cloud and even hybrid cloud is fantastic. And look roadmap of what Slurm could do with transfer queues and other things. I think you're going to see some exciting talks and maybe even some parallel cluster features coming out, down the road, where I think the concept of hybrid cloud and cloud bursting is starting to become a little bit more real. But for me, it comes down to data movement. It's really easy to buy and acquire and leverage CPU. It's really easy for me to burst jobs into the cloud. The thing that gets me is terabyte to petabyte scale data movement. It's the egress fees that kill me. And so it becomes an economic decision more than anything else.
Awesome. And then we just got a +1 for folks interested in the Slurm REST API. So I know you're actively working on some of that. Yeah.
Yep. Yeah. So I think that might be another webinar discussion or maybe a BioIT World Talk or something like that. But yeah, there's definitely interest now with programmatic controls of Slurm, and that RESTful API looks pretty slick.
Excellent. So I don't see any other questions.
Yeah, I think we might be towards the end.
Yeah. There was one question about, which scheduler we typically use, SGE, Slurm, PBS, other. It's worth mentioning that ParallelCluster 3 now only supports Slurm and batch. So if you need PBS or SGE support, you have to use the previous versions of ParallelCluster. Yeah. And I had mentioned this in the intro slides. I'm an old school grid engine bigot. I spent most of my career tuning grid engine clusters. I'm a big fan of grid engine. For me, it was a learning curve going to Slurm, but I can also read the tea leaves. Slurm is basically the de facto standard scheduler in the HPC world. If you look at the US government sites, you look at the US government civilian supercomputing sites, if you look at academic supercomputing facilities and commercial, Slurm is kind of, the clear leader. That being said, I mentioned in my slide, if you do need PBS Pro or you do need Grid Engine, there are other platforms out there. For instance, Bright Cluster Manager can do both. Bright was bought by NVIDIA. You could go talk to NVIDIA if you want a sort of auto. And there are some interesting things about Bright involving cloud bursting and auto scaling that are interesting. But Bright for sure can handle PBS, Grid Engine, or Slurm. And then finally, if you're PBS specific, Altair, I think still has a sort of flexible auto scaling cloud solution as well that would come with support in PBS. So unfortunately, if you need something other than Slurm, you're probably looking at talking to Altair or the Bright people at NVIDIA, I think would be your next viable options other than kind of rolling your own. Yeah, and also I would say, if you're looking at sort of migrating from Grid Engine to Slurm, I have, really look at how people are using the scheduler, because if they're not really using SGE directives in their scripts and stuff, there's actually, wrappers for QSub and QStat that come out of the box in ParallelCluster. So you might be surprised that some of your job scripts can kind of easily work within Slurm if the researchers are only using, QSub and some very limited arguments. So, yep.
And there is a comment here. I'm not sure if everybody can see the comments, but Azure CycleCloud, we know the CycleCloud people at Azure, they're great people, supports PBS. So again, if you have a business or technical need for PBS, Azure CycleCloud, is an option as well.
Great, okay. I don't see any more questions coming in. So yeah, thanks. Keep ideas coming for future webinar topics, and let us know if you have other questions. Again, we'll be sending the slides and the recordings out after this via email. So stay tuned for that.
And I think our marketing people might be anxious about over-promising. So give them a day or two to get the slides and the video out, just so that you don't expect it instantly after this. I think the marketing people are a little bit concerned that we over-promise there.
Excellent.
All right.
Well, we're at the top of the hour. Yeah. Thanks, everybody.
Thanks, everybody. Chris. Thank you very much for sticking around. We really appreciate it.